You are muted, Ashish.
Hello. Can you hear, sir?
Yes, we can hear now.
And start your talk for 25 minutes. We'll keep 20 minutes for presentation and 5 minutes for.
So, is it okay? Shall I start?
Please start. See your presentation again.
Okay, I don't understand quite clearly, but I think it's okay. So just let me. Oh. Okay, so can you see my screen now? Is everybody seeing a screen with 3 houses? Sorry, I can't hear. You are seeing and you are hearing me? Okay, so we'll start discussing about. Sorry, it's okay or?
Okay, please go ahead.
Okay, so I will discuss about material modeling in acoustic absorption and insulation. So I will focus mostly on porous materials. They are the most challenging parts. So here are 3 houses, and we will discuss this in a few slides. And they are in the nature, but usually our houses are not so in this nature like this, but mostly in cities. Sorry, someone is saying something. Oh, okay. Should I continue? I don't understand a word of what you're saying.
We are listening. Please deliver your talk.
Oh, okay. Yeah, so you can see these slides going to apmr.matelis.com, like this one, and you will be able to follow me with the slides. Okay, so I was discussing about these 3 houses. So just to give you some information, so the fact that these houses usually are in big cities, so we are facing noises from different sources like cars or planes, so traffic noise, but also noise from the neighborhood in cities like this. And if we have a straw house, a wooden house, and a brick house, they will have interest, for example, acoustic correction, but not so much for acoustic correction for the brick house. But the brick house will be better for acoustic insulation, and so we will have to deal with complex partitions, which will involve porous materials. Just to give you some figures, in France, at least the social cost for is important for acoustics. So it's estimated to 20 million euros, which is almost 20 million US dollar or 1.6 billion rupees per year. This money is spent for protection equipment, hearing aids, a sleeping pill for people who can't sleep due to a noisy area. And so there's more and more regulations for insulation of buildings, traffic noise, and these regulations are becoming more and more restrictive. So to understand how the sound is propagating through a porous material, first we will have just to have some refreshing of how the sound is propagating through fluid. So we have here a compressional wave, so I'm sure that everybody has already seen this kind of pictures, where we have the molecules on the top, and on the bottom it's just a pressure wave, which is a representation of this motion of the molecules, where we have the higher pressure where there's a compression of the molecules, and we have the lesser pressure when we have dilatation of the molecules. So this is a compressional wave for a fluid. For a solid, we will have a compressional wave like this, but the molecules are more ordered than for the fluid. And we also have a shear wave, at least one shear wave, which is also called a transverse wave. So we show you these two propagating waves from the left to the right. And in the case of a porous material, so which is made of two phases, one is a solid part and another one is a solid part, we will have at least 3 waves when we consider an isotropic material. So there will be one compressional wave which will be linked to the fluid phase. We use it, usually we call it P2 for primary 2. The first primary wave will be the compressional wave linked to the solid phase, and the shear phase of the solid phase will be called the secondary or S wave. So from the animations you have seen before, we will have this kind of 3 waves propagating in a porous material. And if we assume that we will have a motionless skeleton, a motionless solid part, only one wave will be propagating. It will be the compressional wave linked to the fluid phase. In this case, if we have only one wave propagating in a fluid, and we assume that the solid is motionless, so in this case, we can write an impedance, a surface impedance like this, or ZS, which is a function of the impedance of air multiplied by a complex quantity, and this complex quantity is explaining what's going on inside the porous material. So here we see an interface between the air and the porous material. And at the interface, so the forward wave is the blue one. The reflected wave at the interface is the red one, going on the opposite side, opposite direction. And the black wave is the resulting wave, so the sum of the blue and the red one. And in the porous material, we have probably some difference of the wavelengths, which is due to the impedance and the properties of the porous material, and some damping. So we can play a little bit. I can play a little bit just to show you how things are going on if we change the value of the real part of this impedance, and of course the imaginary part is linked to the dissipation. So the higher the dissipation, the imaginary part, and higher will be the dissipation. So this dissipation inside a porous material are linked to different kind of effects, phenomena. So one effect is the viscoinertial one. One part of the effect is the viscoinertial one. So it says at a low frequency we have a viscous flow, and at high frequency we have an inviscid flow. So no really impact of the viscosity of the flow of the fluid. For the thermal effects, we have at low frequency heat exchanges between the fluid phase and the solid phase. So we can say that we are in some kind of hydrothermal regime, while at high frequencies we have no heat exchange between the solid and the fluid. So in this case, we are in a adiabatic regime for this, for at high frequencies. These are the viscoinertial and thermal effects. These are effects which are linked to the fluid, which is bonded by the solid. But we can also have in the solid structural damping. So this is what I represent with this mass spring system. The structural damping is due to when you set into motion the solid part, you can have frictions between the molecules of the solid part, and this friction will cause damping. So just before discussing more about the porous metal and the relation between the microstructure parameters to the surface impedance or the sun absorption, for example. Just a note about the bulk properties we are using. Usually when we are dealing with porous material, we are using two complex quantities, which are the dynamic mass density and the dynamic bulk modulus, so rho and K. They are linked with the characteristic wave number and the characteristic impedance with simple relations, as you can see. And why we are using these two quantities, the dynamic mass density and the dynamic bulk modulus, it's just because they are linked to the viscoinertial effect and thermal one I've just discussed. So rho is related to the viscoinertial effects and K to the thermal effects. So if you know what is the value of rho and what is the value of K of a porous metal, you can understand how your metal is dissipating the energy. So now that we know that we have to deal with rho and K, how we link this rho and K with the microstructure of a porous material. So here is a simple example of a porous material. So in black, this is the skeleton, so the rigid part of the porous material. And in between, you have to imagine that there are straight cylindrical pores. And there's some acoustic excitation on one side here. So this is a very simple porous material. And to describe the dissipation mechanisms inside this porous material, we will have to use one or two parameters, usually two. One is the porosity, so which is usually denoted as phi. The porosity just expresses how many cylindrical pores I have in my porous material. And another parameter can be the radius of my cylindrical pores, or the static airflow resistivity sigma, which is linked to the value of this radius. So if I have these two parameters, I can compute via a model like the Zwicker and Kosten one, some value for rho and K. Of course, most of the porous metal are not so simple, and we have more complicated models with more parameters, as we have more complicated morphologies for the porous metal. So for example, if we have slanted cylindrical pores, we will have an additional parameters, which is alpha infinity, which is the tortuosity node that we call the tortuosity, which is, if you want, the angle of the orientation of the cylindrical pores. For non-uniform sections, so pores with non-uniform sections like this one, we will have to use 4 to 6 parameters. But usually the most used model is the one by Johnson, Champoux, Allard, Lafarge, which is also called JCAL. And there's more complicated model for non-uniform sections with constrictions, where we had 2 more parameters. So from 6 we go to 8, adding 1 parameter for the viscoinertial effect and 1 parameter for the thermal effects. But in this case, it's quite it's quite difficult, to extract the 2 additional parameters for characterizing the material. So when it's not easy when you put a material sample inside an impedance tube, for example, to extract the value of these 2 parameters. So most of the people are dealing with this JCAL model with 6 parameters, because it's easy to put your material sample inside an impedance tube and get all the parameters, all these 6 parameters, and compute rho and K. So how do we compute rho and K from this morphological model? So here is an example for the JCAL model. So you can see that we compute rho and k from the parameters alpha infinity, phi, sigma that we have seen before, and some other parameters like rho 0, which is the static mass of the air, so at rest. Omega here is the pulsation. And we have another expression for k. So I put the reference here of this model. But what we can do is just go to the next slides and play a little bit with some parameters. So here on the right, you can see two curves, curve which represents the sun absorption coefficient. So in black, it's the normal incidence, and in red, it's diffuse sound field for the material with these parameters. So here I set a given thickness and I'm computing the surface impedance, and then after the sun absorption coefficient for a given thickness. And I can play with the value of the parameters just to show you how this will change the curve for my absorption with the porosity. What is the influence of the tortuosity? So it will shift the frequency of the first peak to lower frequencies. And we can play also with the resistivity. And yeah, just to show you what is the impact on the sun absorption, but I can do the same for sun transmission if I want. But the sun transmission of just a porous metal is not so important. So it's probably better to show you directly with this animation for sun absorption. Oh, by the way, if you go to the website APMR, you can play with this and have some more information about this model GCAL1. But for the time being, I will go on with the next slide. And in this slide, so far I've discussed a model. So the GCAL model is for material having a rigid skeleton. So this is what I'm showing here in blue. So this is a model for a rigid skeleton assumption. And I also showing you in this curve, so the diffuse sound absorption for as a function of the frequency for this GCAL model or the bio-GCAL model. And for the bio-GCAL model in orange, I'm just adding the effect of the solid part. So if I'm assuming that I have an isotropic solid part, I will just have mass density, Young modulus, pressure ratio, and loss factor, and I can see what is the impact of these parameters on the sun absorption. So one can imagine that the effects are not so big when the skeleton part is set into motion. This is true, but only when you have a low resistivity, because when you have a higher resistivity, you will see that the impact between the model assuming a rigid skeleton and the one taking into account the motion of the skeleton, the motion of the solid part, can be much higher than that. Okay, so here's another example. Again, if you go to the APMR website, you will find a MATLAB GNU Octave script to compute the coefficient of sun absorption for normal incidence, because for diffuse sound fields, it's it requires another type of metal, more computational. And I will not go on to these details now. So just in my two last slides, I just want to discuss what are the perspectives or what people are working on about porous metal, in addition to using natural materials, as we have already seen in the presentation this morning. So common wave phenomena in building acoustics we are using are reflection, so refraction, transmission, and absorption. So we have seen most of them in my previous slides. But people are trying to add some more dissipation by adding some more physical phenomena, some related to waves, other not related to waves. So they are calling them metamaterials, but you should better call them multiple dynamic materials, in the sense that we are adding to the viscoinertial effects and sometimes the structural damping some more effects like diffraction due to some change in the shape of the porous metal, scattering when you add solid inclusions or other kind of inclusions inside the porous metal, dispersion. So we have seen that rho and k are a function of the frequency, but you can also take into account or add some dispersion inside the solid phase. And for the absorption, this is not a wave phenomena, but this is a mechanism made of adsorption and desorption. So here we see desorption, and adsorption is the possibility for the solid part to glue, if you want, the molecules of the fluid. And this is what we find, for example, in activated carbon. And in this case of activated carbon, we can see that the absorption effect can add some more dissipation. And so we have a better sound absorption or a better sound transmission for material, for partitions involving porous material like this. So here is the last slide for my presentation, and thank you for your attention.
Have any questions? Like, I have one question, sir. Taken a number of parameters to see their variation.
So sorry, can you speak a little bit louder?
Hear me now?
Yes, a little bit more.
Is that better?
Yes.
So you've taken a number of parameters and showed their variation on the absorption coefficient. But when you are using these better materials in your panels or as porous materials, would the ambient temperature not affect their performance? Like in a hot country like India, where the temperatures can go up to 110 Fahrenheit or maybe 45 degrees centigrade, would the absorption not be affected?
If the absorption will be affected due to the temperatures, you mean?
Variations in temperature.
Yes, but very softly, because the only impact will be on the parameters of the air. So rho zero, for example, but it will not be a very very impacting. So it's not a big deal, and everything can be adapted at least to high temperatures and high hygrometry.
Thank you, sir. So there are no more questions. Let us thank Mr. Duke Joel. Thank you so much, sir, for your for giving time and giving this excellent presentation.
Okay. Thank you for the invitation.
I'll go to the next presentation, which is by Mr. Tom Lane of Vanguard Technologies, Australia.
An international business manager with many years of experience in the noise and vibration field. He has worked with multiple industries, including airport, construction, mining, and general industries, to assist and provide solutions that meet their business needs, improve environmental noise compliance, reduce operational costs, and better community engagement. Mr. Kum currently works for Vanguard Technology and specializes in real-time noise mapping. Mr. Kum holds a Bachelor of Mechanical Engineering, member of Australian Acoustics Society, and is a regular guest speaker at major conferences.
Mr. Tom Lane. Online.
Good afternoon. Can you hear me?
Welcome to this conference, and thank you for giving your time. You can
Beautiful.
share your presentation and give your time.
Thank you. Thank you for the warm introduction, Ashish. Let me just share you my screen now. Just one moment. Okay. Can you confirm that you can see my screen?
And we can hear you clearly.
Fantastic, fantastic. Yes, look, first of all, I just wanted to thank Dr. Naveen Garg for inviting me to speak today. As Atish mentioned earlier, my name is Kung Nim, and I work for Vanguard Technologies. I just wanted to pleased to be able to come today and present on the new technologies for noise modeling. And today the talk will be about the dynamic noise mapping and the approach on solving some of the noise challenges, and also looking at how this can affect the Indian the effect of noise challenges in India. Before I start, I just wanted to share with you some of the latest developments in the environmental management evolution, as you can see on this slide here. So where industry typically in the environmental management plan, typically you start with monitoring. And now I know in India and other parts of the world, has been extensive monitoring has been done, but the move is more closer to a business driven in terms of using how do I use that information to make business decisions, or cities doing mapping, for example. How do I use the data to understand the impact a lot better on the community? So that would involve in a migration or an evolution, I would say, from a first generation, second generation to a more third and a fourth, where there's some modeling is involved, and in forecasting what those noise impact will look like, so that you can, so people will use that to you manage compliance or to understand the impact on the community, and to look at ways to mitigate the noise impact on the community. And having that information is quite critical. And the next part is sharing. How do I share that effectively with my stakeholders, whether publishing that on website or selectively share that with the different stakeholders to understand what steps needs to be taken as part of the next planning. So this is where we're seeing the technologies is evolving. You can see in the approaches to solving noise challenges. So the as I mentioned on the previous slide, so the generations is progressing more to the right-hand side, where we're seeing modeling is starting to take place. We're seeing static is being done already on terms of planning, using the model to understand the impact on a future scenario. But can this be improved? Can the modeling be improved to make it more dynamic? So as you can see in the context of India, CPCB has done a lot of monitoring, invested in a whole network of noise monitors. Really, the challenge is understanding what are those contributions. Is it which region is causing a lot of the noise, and how do I reduce that, and what sort of mitigation measures? Now, the only way one can do that clearly is to migrate to a mapping system, and whether it's static or dynamic. Certainly in a dynamic world, you can see the changes more often as the data sets is being updated. So what is noise modeling? So noise modeling is really is a tool that business or engineers use to predict the noise impact, and they would use that to understand, compare against the legal guidelines of the noise limits, so that you can meet that, or you can take actions on how to make control. So it's a visualized tool over large areas. The contour is very visual, so you can show the impact of new areas to be constructed. So particularly if you're putting a new road or a new industrial area being developed, it would be beneficial to do a noise mapping so that you can understand the impact, and then you can take corrective actions. How do I mitigate whether you put noise walls and things like that on a freeway? But it's a great tool for planning and mapping of the area to do the study, and also it gives you the ability to quantify the sources and identify what's contributing to the noise. This technology has been around for a while, and in Europe and Australia and other parts of the world. Similarly, in India, I'll share with you the next slide what India is doing in the noise modeling. But the methodology is known, and you can do calculations using the empirical methods or the theoretical methods, and that's based on certain standards that's been predefined, either for road and traffic, curtain noise, ISO for industrial, or other methods that's listed here for different scenarios. The challenge with noise modeling is really they can overestimate. So getting that data accuracy is a challenge. It's really depending on the inputs. So estimation can happen, but most importantly, these are static. So these needs to be done and updated on a regular basis if you're looking for a system that's going to be meaningful, so you can make informed decisions in real time, or looking at the progressions and how the noise has changed over time. And they are not integrated with other data sets. So data sets are becoming available. A lot of data sets are now becoming available. So you can actually integrate that and provide a complete picture in real time as part of the technology enhancement. If you look at what India has been doing, and this is, as I said, India, there has been a lot of studies on how the impact of noise modeling, as part of that upsurge in noise pollutions, particularly in mine sites. We do a lot of work in the mine site as well here in Australia and other parts of the world. Modeling will show you the operations, how it would look like in the hotspot, and then how you could change if you are rerouting or certain machines is causing the noise problems, and having that data sets available from this different part of the department is important to collate that to make a very more accurate noise map that business can make decisions. So for planning new mines or starting a new shift based on the weather, so the weather can change, whether it's a temperature inversion, that has an effect on the noise. So that's important to model. So we, as part of moving to a dynamic system, these data sets is very important. So the challenge as in getting the data in India, for example, or in other parts of the world, is that can we move this to a dynamic system? And the answer is yes, it can be done, but the availability of data is very important. So having access to data availability, like the GIS data, or the live traffic. If you're doing a traffic calculations, getting the live traffic and update and counts is important. So that's always constantly refreshed and updated. Likewise with the weather information. So having that whole data sets is important. Plus, consideration has to be made for calculations methods that is reflective of the local conditions. So that could be traffic conditions in India with honking noise and other noise sources and drivers' behavior. So these are important factors in understanding and putting a right dynamic map together. In terms of how to make it progress into a dynamic system to make it work, data sets are already available, and SCADA information, for example, if we look at a fixed plan, these are data sets are available with the GPS data. So I'm hearing some noise at the back. So data sets like GPS data is certainly available, and that can be imported into the model, coupled with all the environmental data sets. So for noise monitoring, so you can use that to validate and compare the model that you are predicting. Having a continuous feedback is important. Likewise, the live weather systems. By putting all that together and putting into the noise model, you can use that data to share with the community if need be, or other stakeholders, so that you can understand the impact. And that's really looking at levels, noise levels, impacts down to certain levels of certain machineries and so on and so forth. So that will help in identifying a more targeted approach in understanding how do I control my noise. So for example, in the mining space, a lot of the machineries will be taken offline to do conditioning monitoring, for example, or some sort of noise control in terms of abatement process. Now, what would it look like? In the context of improving some of the early studies in India for the noise, the open cast mine. As I said, this technology is now available. It's really looking at the next step. And that next step would look like something like this, and that's really providing an outcome so that they can understand and manage compliance. So what you see here on the screen here is a dynamic noise map that is calculated in real time as a function of the speed of the mobile sources. So the red dot you can see on the video is actually showing the truck moving up and down. So this is a representative of a mine where we're taking the fleet management system and the noise emissions, sound power levels of all the equipment is modeled, coupled with the terrain, the topography, and also the weather conditions. So you can see if your operation is impacting on the community, and you can send alerts and alarm with traffic light indicator as such to demonstrate that you are operating. So it's a very visualized tool, and it's dynamically changing, and that's will be an added advantage. Other areas you can see here, as in refineries or fixed plants, again, a lot of the noise changes as a function of the weather. So certainly by the model of the site with all the machines on and off, you'll be able to identify the contour and manage the noise much more effectively. So lastly, as mentioned earlier, dynamic mapping is certainly a tool that is available in the technology to help manage. And here we are taking on a port where there are more conveyors going on and off, different operators. So you have the ability to identify your noise source much clearly, coupled with the changes in the weather. So what would that mean for India? I think this, as the legislations or the development moving to the new phase, certainly, having a model to start it in a mine site, for example, or in other ports, but certainly will give you more visualized indications of the noise source. And that's all I have today. Just wanted to share that with everyone. And if you have any questions, please feel free to ask.
Thank you, Mr. Paul. Questions, please? Dr. Naveen Garg will be answering the question.
No questions?
There is one question coming up, sir.
Yeah, hello, Kung.
Hi.
Are you able to hear me? Hello.
Yes, I can hear you.
I have one question actually. How do you think as dynamic noise mapping is a quite cumbersome process as compared to the static mapping? So do you think it is practically feasible in Indian scenario to adopt such a model? Because every time you are generating a different map and then you have to take the actions plans accordingly. So I think it is a very difficult process in Indian scenario as compared to that in the European scenario.
Yeah, that's a great question. I think if you look at, as I mentioned earlier, in the Indian context, some of the mines are starting to look at doing modeling for their operations already. So, for example, if they are, the static to model dynamic system is not as complicated. Well, I wouldn't say it's not complicated, but the process will be the same as doing a static model. So the models that already done using the existing flyover map or the data sets available, we can import that into the model, and then really the changes, most of the mines do not change very much. It's more about the weather changes that can have impact on the noise. So the process will be the same, taking the data, or if they've got an existing model already, that model can be imported, and then we overlaying all the other data sets that's critical into the operation.
Okay, thank you, Poon.
No problem at all.
Any more questions?
Any other questions?
I have one question.
Yes, ma'am.
You have mentioned that in the modeling, using static models, they tend to overestimate and they're not integrated with the data sets. So in both the cases, in static as well as dynamic modeling, how is the validation done?
Again, that's a fantastic question. So that's right. In a static model, it tends to be overestimated because there's a lot of assumptions being made. With a dynamic model, we are taking more data sets. So for example, in the SCADA informations are available, the GPS is available, so the sound power of all the noise sources are known. So we import that in, and we use, coupled with the noise monitoring that is done, whether it's attendant or real time, that information is used to feed back into the model for calibration of the system to make it accurate according to some of our works here at the mine sites. We've done a correlation to be within the 1 dB of accuracy.
The correlation in static models?
The correlations to the measured. So the measured, so the monitoring is important. So that's in that generation 2, as I mentioned earlier. Most of them mine started with the monitoring. So if you want to understand your contribution, you go out there and do a measurements. You stand there and do some measurements, and you can see the noise sources. So the validation of the prediction is against the measurement.
Thank you so much, sir. And thank you for your time and an excellent presentation and very clear explanations.
Thank you very much.
Let's thank everyone on behalf of everyone here. I personally thank you for your time.
Thank you. Much appreciated.
And now we take
Have a good afternoon.
Our next presenter is Mr. Kevin Cornier from ACOEM France.
Mr. Kevin Cormier is the global business leader, noise and vibration line of business in ACOEM and based at France. He has more than 17 years of experience in acoustics and is associated with ACOEM since 2006. He'll share a presentation on strategy of noise mapping and monitoring.
Kevin is actually not present here and online also is not available. He has sent his recorded video because parallelly there is an inter-noise going on in Glasgow, Scotland. So he's there. But,
So we'll have a recorded presentation here. We'll start with your questions.
to combat noise pollution and protect quiet areas. This directive has three objectives. First, harmonize assessment within the state and define standardized indicator. So this is LDN and LN. So second, implement action plans which aim at preventing the effect of noise and reduce exposure levels if necessary, and identify and preserve the quiet areas. Third, inform the public and involve the public in the decision-making process. In 2007, all cities with more than 250,000 inhabitants must have noise map for their territory. In 2008, noise exposure prevention plans should be completed before July. 5 years later, in 2012 and 2013 respectively, this process is updated and extended to agglomeration of more than 100,000 inhabitants. And since then, every 5 years, authorities have to produce and update and report their noise emission and reassess their noise exposure prevention plan. So it was the case in 2017, and it is the case now in 2022. This is the virtuous circle initiated by the European Directive of 2002, and whose fuels are the excellence of information and data and the transparency of the policies carried out. The European Directive paves the way of implementing the structure which enables authorities. Such structure, either public or private, are often known as noise observatories. Noise observatory have three missions. One, get the relevant data and analysis to understand the phenomena involved in noise pollution. Second, draw assertive plan and orient public policies. And third, feed authority and public with KPI to monitor the effectiveness of the decision and investment done. For their mission, Noise Observatory use mainly three tools. Field measurement with sound level meter or noise monitoring terminal. It is the only way to characterize accurately the noise and its variation over time. Noise modeling, based on proven computational model of noise source and sound propagation, it is possible to produce noise map to visually identify a large area, critical point, and quiet zone. Finally, public survey, combined with the two other methods, it is a powerful source of information to take into account subjective feelings and socioeconomical aspects. In the next slide, I will detail the challenge and ins and outs of noise monitoring and noise mapping, starting with noise monitoring. The objective of a noise monitoring network composed of permanent monitoring terminals used as reference station to evaluate noise evolution over time and non-permanent terminals for specific analysis and survey is to produce relevant and understandable information for all in the form of statistic and graph. The process of transforming noise measurement to information can be split into three main steps. Get the data, value the data into information, and finally, share this information. A monitoring network for a city like London or Lyon produce every year tens of billion of new elementary noise data, sound level per second in dBA, level per frequency band, or even noise recording. All this data converge to a cloud or local server. The challenge here is certainly to master this uninterrupted flow of information and guarantee the completeness of data. Fortunately, in the past year, huge progress were made to increase the reliability of solutions and services of both sensors and IT infrastructure. On-the-shelf solution exist, and this is no more a pain. The second step is value the data. Transforming this huge amount of data into relevant information and insightful synthesis is certainly the most critical challenge for a noise monitoring engineer. Make the most of exploration and analysis technique is certainly the key. More and more embedded algorithm with advanced signal processing like noise source recognition is supporting experts. This is actually the lever which have to be triggered to get efficient analysis and shorten the path between measurement and action. It is for this key step that specific knowledge of the context and the location must be present to extract relevant information from the monitoring. And it is also for this step that acoustic expertise is mandatory. The last step of is the representation of the data and the setting up of the communication channels. Data visualization remain a challenge, especially since this communication and the message must be established at different levels for stakeholders, authorities, and citizens. For data sharing, performing solutions exist, dedicated platform, public website, and communication protocols are available to share data with a very wide audience. So in summary, the key elements for the data valuation process is the addition of expert skills, namely acoustic expertise, and knowledge about specificities of the local habits and local behaviors to existing expert solution, reliable and recognized, that ensures the most efficiency and relevance from data mining, data engineering, and data visualization tools. The other challenge are now largely mastered by recognized players in the sector, and in particular, ACOM. A noise map is made up of sound levels curves, which make it possible to assess the exposure of population to noise generated by transport and the most important industries. A strategic noise map, as defined by the European directive, is composed by three elements. One, a graphical representation, usually called maps, which show on the territory the sound levels or the area where certain thresholds are exceeded, generated for each of the noise sources studied and according to the indicator required. Second, a statistical tables giving the number of people and sensitive establishment, like school or hospital, that are exposed to noise. And third, a non-technical summary which succinctly presents the tool, method, and data used, and which provides a summary of the result. The noise map only reflects the exposure of population to noise generated by road transport, rail transport infrastructure, and air transport, and also noise activity from industry. The other source of noise of a more or less fluctuating nature, for example, neighborhood noise or sound emergence from such as horn or construction site, are not represented. The map also do not apply to noise perceived in the workplace and inside transport or laser noise. A noise map is not the result of on-site measurements, but of computer modeling carried out using data descriptive of the topography, so the relief, the buildings, and other obstacles, and noise source, in particular, data flow from transport infrastructure, speed, a ratio of heavy vehicle, road surface, rail characteristics, etc. This data has to be collected from multiple stakeholders. The production of a noise map requires the collection and the structuring of this input data. Then producing a digital model before launching the computer calculation. And it will make it possible to estimate the sound emission of a noise source and evaluate the sound level on a wide territory, taking into account the law of the propagation and reflection of the noise. So during the computation, you compute horizontal grids for each noise type, and total noise from the transport and industry. Then you compute also the noise level in the facades of buildings. You can import or estimate the number of inhabitants for each building, and then you compute the distribution of inhabitants versus the level of noise. Noise measurement in the field can be carried out in addition to check the consistency of the model, and you can access to additional information, variation in noise over time, for example, or the presence of other important emerging sound. That's it. The main challenge here are first, set the expectation. The model and the resulting noise map only reflect the noise source included. Keep in mind what a strategic noise map aims for. Second, the relevance to get the relevant data from of several stakeholders is a journey. You have to find the right compromise between the effort to get the exact data and the uncertainty of an estimate. The third challenge is to structure and organize very well the database, to automate the update, and to save effort in the refreshing process. To finish my speech, I would like to do a short summary of the ins and outs of noise mapping and noise monitoring. A noise mapping aims for infrastructure planning, scenario evaluation. This is the right tool for impact study for operational sensing, for instance, where noise monitoring is the only way to objectify nuisance, to measure progress of an action plan, and to highlight and point out responsibility. This is also demonstrated that noise monitoring is the right tool to inform public and decision maker, as it's very much appreciate a measurement than a simulation for this purpose. Which noise as considered? Noise mapping consider only industry and transport infrastructure, air, rail, and road, where noise monitoring consider all the noise. It's not possible to filter, and you have the same infrastructure, transport noise, and industry, plus construction, impulsive noise like horn or even dog barking. The parameters and the evaluation period for noise mapping are energetical indicator like LDE and per noise source category, and we consider as a evaluation period a yearly average of noise. Noise monitoring can also extract some long-term energetical parameter, but you have also the descriptor of event, so emergent, for example, the number of event per certain period of time. So it's for long-term and short-term monitoring, useful to identify patterns, seasonalities linked with inhabitant behaviors. Noise mapping suits to exhaustive description of a territory where noise monitoring only apply on the local where it is implemented. As a conclusion, you have understood that noise monitoring and noise mapping are two complementary tools. Noise mapping is for planning, and to plan is to manage. Noise monitoring is key to understand and measure progress or infraction. One can only control what he understands and monitor. Thank you for your attention. I hope my contribution have had some value. I wish you an excellent end of the event. Goodbye and take care.
Thanks for this question. I think clear demarcation between mapping and so now with that please thanks to you. Now we go to the next speaker. Satish Lokhande from CSIR DE, Nagpur. I hope he'll be presenting in person.
Online.
He's online. Okay. So please introduce the speaker.
Yeah. Engineering Satish Lokhande. Satish K. Lokhande sir is presently working in the sophisticated environmental analytical facility as a senior technical officer. Since November 2000, he has developed expertise in the operation and maintenance of sophisticated instruments, total organic carbon analyzer, and CHNS elemental analyzer. He has over 20 years of experience in the operation and maintenance of analytical instruments and environmental impact assessment for noise and vibration component as CSIR Nagpur. He is also a NABET approved field area expert for noise and vibration components and in the charge of NABL accredited noise lab. He is life member of Acoustical Society of India, International Association for Water, Environment, Energy and Society, and Institution of Engineers. He was the recipient of Outstanding Technical Officer Award for his outstanding contribution in noise and vibration studies for the year 2014.
Hello. Hello.
Yes, please.
Yeah, my screen is visible.
Yes, you are visible. You are
Yeah.
visible also. You can go ahead with your presentation.
Yeah. Oh, good afternoon, everybody. So today I am going to touch one topic called road tunnel noise. Actually, this road tunnel noise were regarded as most feasible and effective measure to combat traffic noise. But however, there are certain concerns that I raised here in my presentation, so that whereas people attending the event could have the attention on this, and more studies could be done on this regard. Okay. This is the road tunnel generally constructed to combat traffic noise. These are the positive impacts of road tunnels. when generally preferably utilized in the cities and urban areas. The road tunnels are considered as more feasible, effective solution to sort out traffic problems by diverting vehicular traffic and minimizing travel distance. Tunnels also offers urban mass transit systems that are considered as safe, ecological friendly, and quick. Road tunnels reduce vehicles from street, decrease traffic noise, minimize air pollution, and facilitates authority to utilize surface street spaces. Railway, road, highways, public utilities, and telecommunication benefits from tunnel. Consequently, buildings of road tunnels for transportation corridors growing all over the world. However, there are certain negative impacts of road tunnels are also there if it was not constructed considering the safety and design standards. Then it may also create some problems related to environmental pollutions. As like under specific circumstances, the noise level near the tunnel corridor can be higher than the noise levels at the tunnel entrance section. Just I am showing you the case study, and before that just I am giving the background of road tunnels so that that case study could be properly understood. The noise inside the long tunnels have an average noise level of 90 dB to 130 dB. That is been reported by various researchers. And even when the drivers is exposed to such a high noise level, there is a likelihood of traffic accidents because that kind of pressure is exerted, experienced by the driver. The standard guidelines for road tunnels do not specifically mention the allowable noise limit inside the tunnel, because in the tunnel there is a very high noise due to vehicular noise as well as reverberation noise. Hearing loss becomes a substantial risk factor due to this exposure. You could see the international and national scenarios where these road tunnel corridors have been developed. So you could see in Western countries and other all over the world, long tunnels up to 24 kilometers have been developed at different countries, and in India as well. Construction of tunnels are growing day by day and year and year. There is a effect of noise is also depend on the length of the tunnel and the dimensions of the tunnel. As like here you could able to see some as like FHWA, the international agency, and other agency which have used sound plan as a modeling software to calculate the effect of length of the tunnel on the noise radiation. So here you could able to see they have applied this on a tunnel which is a 15 to 15 meter width, 6 meter height, and tunnel length they have considered 15 meter. So there they found there is a negligible effect on the road noise radiation. However, if it is uh, implemented for the same height and width of the tunnel, but length of the tunnel increases from 30 to 150 meter and over 150 meter to 1000 meter, you could able to see that approximately 0.03 dB of radiation noise per meter increases. And if length of the tunnel is 150 to 1000 meter, then you will have the 0.002 dB of radiation of noise per meter. So this is due to reverberation that added in the tunnel. We can look after the safety guidelines of different countries, national, prestigious national and international agencies, what they say about. If you go through all these safety guidelines, you could find they specifically tell about the design and the safety of the standards of the tunnel, but they are very generalized when concerned with the abatement of noise or what would be the allowable limit uh, uh, to be there for a tunnel of different length. that things I have gone through various design standards. We, I could not able to find just a generalized idea. So that I have put it here. What they say what then traffic operation and control system for smooth maintenance of the vehicle riding through the tunnel. And similarly, the safety requirements like blinking red light, variable text sign, barriers, fire detectors, restrictions on tunnel use, speed limits, that somewhere mentions actually. Uh, and if the important aspect here, the attributes that control of environmental issues, air pollution, noise pollution, you could able to see here. Indian Road Congress standard safety guidelines are is there, and if you take FH, then here uh, very generalized terms you could able to see air pollution emission should be checked weekly. A noise generation standard applicable for construction equipment, machinery, and that about the Indian Road Congress talking about noise to be controlled during construction of the tunnel. But after establishment, they won't speak anything. Noise monitoring should take place monthly. And if FHW says in planning of a tunnel, the construction impact on the community and the environment is important and must be addressed. But at which level it should be considered as violated or not, no standard provides any information. So there are various models that were used to predict the uh, noise at tunnel portal. So most one of these three models I have taken because these three models were used on a field to demonstrate the accuracy and acceptability of the uh, model. Otherwise, most of the theoretical models are there, but they were not practically used in the field. So I have taken these models where AS, ASJ model 2000 developed by Japan. It is used for semicircular and rectangular tunnels. They consider two sources. One is point source that is generated through the vehicle, and other is diffused sound source that is generated due to the reflection and reverberation of the sound. So they, based on this, they predict the noise level. So here uh, they have validated this model in for a tunnel which is a 600-meter length. They have considered absorption coefficient of 0.04 and directivity of 0.1 and 1.6. So they got this result. Their accuracy is less than 2 dB, and it is applicable for road traffic noise around tunnel with no noise control of absorption treatment on the wall. Okay. As like similarly, Germany has uses RLS 90 CADNA modeling software. So it is applicable for rectangular and semicircular tunnels. They consider source as a in the tunnel is a point or area source, and they have studied this model for 50 to 500-meter length tunnel. They have taken absorption coefficient of 0.1 to 1, and they say applicable for both railway and road. Similarly, China has also discovered one theoretical model, and they demonstrated it for semicircular tunnel. They consider line sound source of the tunnel at the center line. They consider it as a line source rather than point and area source. They have implemented this model for a tunnel of length 3,100 meter, 100 meter, and they have taken absorption coefficient of 0.06 and directivity of zero point 0.2, and they say that accuracy is less than 1 dB, applicable for super long term tunnel as well. and applicable to noise reduction design. These are the models which were practically implemented, and the accuracy they found is I have demonstrated here, summarized here. So in my study, I have used this ASJ RTN 2013 model. This is the equation by which, as I earlier told, they consider two sources. One is imaginary and one is a direct source. One is for reflectory and the sound generated due to reverberation of sound, and one is from the vehicle. That is a direct source. And then they uh, explore this with different calculations and finally calculate the uh, LAEQ at the predicted point. This is the actual site where we have tested this model. This is the actual picture of the tunnel. This is a single tube tunnel, and allowed for both kind of traffic in and out. So you could able to see the sketch of the site where at inside the tunnel as well as outside the tunnel, and here at 3 meters our receiving point is there where we have monitored data and as well as predicted at this point. So you could able to see 6 locations are there, and this is the 7th location where noise prediction is taken. We have calculated with using this ASJN model. So this is the actual aim of the study. We want to see the applicability of the ASJN RTN model, whether it is applicable for Indian conditions or not. We have also investigated the acoustic characteristics of noise inside the tunnel by analyzing its octave frequencies, and also correlated whether it is relates to noise-induced hearing loss or not. The people health effect on the pedestrian walkway through the tunnel, that also we have seen. These are the site observation. This the tunnel we have considered is 500-meter long. It is 6.5-meter width and have 8.5-meter outside the tunnel. Okay. Uh, Noise community noise honking from vehicles and various modes of transportation, such as two-wheelers, three-wheelers, cars, sirens from ambulance and other light vehicles are all the sources of noise inside the tunnel. Pedestrians also using the tunnel for passing and no separate way for them. It took about 8 to 10 minutes for the pedestrians to cross the tunnel. So till that time, they exposed to high excessive reverberation sound. No any sign of speed limit at entrance and inside the tunnel. Road tunnels reduce traffic from the area which they pass, but increase the noise level inside the tunnel due to its reflective walls. No any guidelines on emission of noise inside the tunnel road. No any previous study found on road tunnel noise in India. These are the findings we got when we have we have completed the study. So these are our findings. Noise level monitor inside and outside the tunnel at 7 points. The ASJ RTN model we found very fit for Indian conditions, as we got only 0.4 to be difference in measured and predicted noise level. The noise level at the receiving point we measure is 85 dB, and whereas the predicted noise level computed was 84.58. So this is very applicable model. Noise level at all 7 locations found above 80 dB, which correlates with NIHL, noise-induced hearing loss. The investigation of the frequencies spectrums also reveals high sound pressure level at 4 kilohertz, and around this frequency is related to noise-induced hearing loss. These are the graphical analysis we could able to see. This is the permissible limit, as if we in India road noise is considered as a commercial activity. So 65 dB is the allowable permissible limit, and you could able to see we have compared with different noise parameters, LAEQ, LAF max, LC peak. So you could able to see it, they are drastically much above the permissible limit. Similarly, if we take the statistical values, then you could able to see that they were also as much as high as compared to your permissible limit. One city environment quality review criteria. It is an international agency that says if LEQ is approximates to L50, then the noise is not insignificant, right? The noise we observed is not insignificant. But if LAQ is approximately equal to L10, then it is broadly significant. And if LAQ is approximate to L90, then it is extreme. So in our study, we found our noise level is within the broader area, the significant broadly. So due to which this graphical slides I have kept. So here you could also see the spectral analysis of this. These are the spectral analysis of the noise level that is outside the tunnel. You could able to see that everywhere noise levels, higher noise levels are very close to 4 kilohertz frequency. So they most of it are correlates with the noise induced hearing loss. Similarly, if we take inside the tunnel, there also you could able to find that dominant frequency is around 4 kilohertz in most of the time. So this also see that it correlates with noise induced hearing loss, and definitely will going to affect the pedestrians or cyclists or tricycle users, that they get exposed to such extreme noise and may have a chance of partial or permanent noise induced hearing loss problems. So this is at the place where a noise has been, that is the receiving point. So these are the recommendations our study gives. As the difference between measured noise level and predicted noise level was found 0.42 dB, which is highly acceptable, and recommends that the ASJ RTN 2013 model is practically applicable for Indian circumstances. As it is found in many published literature that sound level inside the tunnel ranges from 80 to 95 dB, this study recommends forming separate noise limits for road tunnels to protect the pedestrians, bicyclists, and other similar riders commuting through the tunnel. The study recommends complete restrictions of honking inside the tunnel. Considering the commuter safety perspective, the road tunnels above 500 meters must have separate walk side for pedestrians with a barrier. This is about my case study, and now I am going just give the glimpses of one noise app. Last time in the same workshop, actually, I have discussed about uh, the app we have developed for noise measurement. That is noise tracker app. That is a time-based noise app. But now we have come up with this is the last app which we have discussed in the last conference. But now we have come up with these are the users all over the world for this noise app, and this time we have come up with a very advanced noise measurement app using mobile. This name of the app is Noise Tracker Pro. Here you will get, these are the features. You could able to calculate L10, L50, L90. You have 1:3 octave graphical analysis. Even that data you could see in your tabular form. You could able to share that data. You could have calibration. You could have transfer of and sharing of files using any type of any kind of app you could able to use, any kind of features you could able to use. So lot of everything as noise meter is having everything this app can able to provide. If I have did the analysis where I could able to find that till now only 9 to 10 countries have developed a weighted noise app, and ours is the 11th app. So you could able to find from this uh, slide that many of these apps are not free; they are chargeable. They are paid apps, but ours is free. Just for the sake that we want to create awareness in India and everywhere, and for the academics students, they should have a handy tool to use the app for their research purpose and for noise awareness. So you could able to see here. This here you could able to spectrum. Um, See the octave frequency graph. So real time graph you could able to see for your measurement data, and even you could able to have your frequency analysis graph as well as that. Similar could be found in tabular form. This kind of feature you will not get anywhere in any of the app, because many of the apps were having frequency analysis this spectrum, but not they show the data as well for using user purpose. So this we have kept. So it is my request to use it and give your feedback. Thank you very much. Thank you. Hello.
I'm audible, sir? Please, sir.
Hello.
Satish, sir.
Yeah.
Yeah, Devendra here. So actually, I have a question because I have seen your study where the maximum sound which you are showing in the tunnel, which is 80 to 95 dB,
Yeah.
which you have got in your study. So my
Yeah.
first question would be like, what is the permissible limit for a tunnel? Will it depend upon the length of that tunnel or anything else parameter? What is the permissible limit basically?
Actually, what is my experience is for long tunnels. Actually, there is a implementation of some. So there is some restrictions actually for pedestrians generally, and two-wheelers are not allowed to enter the tunnel. Actually, this problem exists in tunnels of a medium range, say 400 to 600 meter or 700 meter. Actually, so there. Uh, permission instead of some permissible limit, actually there should be some safety protection should be there for the pedestrians or the walkers and commuters and two-wheelers, and that there should be a separate lane for them that should be covered so that they should not be exposed to such excessive noise level.
So that sound 85 to 90 dB should be in the range of 55 to 60. Any particular value you recommend for panel, or it is only for the like instruction which you are suggesting them?
I actually brought out two things actually here. Some allowable limit should be there, as like because the safety guidelines say that noise should be regulated as per the standard. If we go to the standard, it should be 55 to 65 dB. And I think that is very difficult uh, uh, to to control that noise level within the tunnel. That is definitely sure. So at least it should be up to industrial standard, that is 75 dB or 80 dB. That should be there.
So my next question will be like same related to this point. So what type of material you recommend just to absorb this particular high sound in terms of tunnel construction?
Uh, uh, there are actually a lot of material studies have been did. I have gone through various literature. So absorptive materials were recommended for most of the tunnels, but by coating of absorption material, I found is much effective than other strategies used in the tunnel so far.
Thank you, sir.
Any other question?
Hello, sir. How are you? Basically, in a tunnel, whenever there's a vehicle crossing, there'll be not one vehicle, there'll be multiple vehicles. And whatever the horn noise will be definitely more than 80 decibels. In that case, and when there are multiple horns, they'll definitely go up till 90 decibels. It could because the reverberation time will be very high.
Yeah.
So don't you think we should have a parameter for reverberation time in the tunnel to ultimately get down your decibel levels to whatever maximum is achievable, because there is a limitation of it.
Yeah, actually, as like in long tunnels, actually, they use some ventilation holes are there, and they use fans as well there. As long tunnels are there, they use jet fans and all. So here also such a technique could be able to use, so that noise inside the tunnel will be reduced by venting through certain vents, so that the noise inside the tunnel will be less. Actually, when long tunnels were built, they take actually lot of measures actually, but they such tunnels are not existed in urban areas actually. They were existed somewhere in the terrains or all. But in urban areas, there are, if you see in the cities, there are lot of tunnels actually. Lot of tunnels, 400 meter, 500 meter, 600 meter, crowd of.
Are we aware of what is the reverberation time presently? Do we have data on that?
Yes. So that that reverberation time could be controlled if we give some ventilation for it. So that noise will get reduced.
Thank you.
Hey. Am I audible to you? Hello?
Hello?
Yes, I have one question.
Yeah.
You have shown the results of your predictive model, but
Yeah.
for the tunnels that are already established, how useful is this predictive model? Is good monitoring and mapping be not more useful?
No, actually, there are models actually, but they were rarely used actually, because as I said in my presentation, that tunnels were highly considered as a best noise control measure for urban transport actually. So due to which actually there are very rare studies, less studies were conducted on road tunnel actually. So there is a need to have more studies on this, and some kind of problems, issues related with the noise should be brought up, so that these could be properly implemented, because the safety measures and allowable permissible noise limits, that should be implemented.
Thank you. Thank you so much, Mr. Ravi.
Yeah.
One question, please.
Yeah,
Yeah.
there is one more question, sir.
Yeah.
Good afternoon, Mr. Lokhande, Rajshekhar.
Yeah. Good afternoon. Good afternoon.
Yes, sir. Sir, Actually, it's two questions. A
Yeah.
is when you look at a tunnel, you could also have vibration inside it when the when a car moves or when.
Yeah,
Have
yeah,
you
yeah,
done
sure.
any studies of something like a structural borne noise where you are comparing noise and ground vibration at that time to see whether the noise is coming not just due to the vehicle but due to vibrations inside the tunnel when a large truck is going or anything.
Yeah.
So that is one question. The second is the fact that the tunnel now becomes a highly diffusive area with all the reflections.
Yeah.
A normal sound meter microphone is used for free field measurements.
Yeah.
Now you are no longer in a free field, you are in a highly reverberant field. So should we also look at using a different microphone rather than a normal free field microphone? Because you will have errors in the microphones at these frequencies.
Yeah. Actually, in this regard, actually, it is recommended to have real-time noise measurement and vibration measurement devices should be implemented while the constructions of this tunnel, so that regular informations regarding the tunnel noise and vibration could be collected, so that it will benefited in two ways. One, we will get the noise and vibration data in a real time, and a similar way, structural analysis also could be done along with this, because we are getting noise vibration data. Actually, as per the standards, if you go through various standards, they have recommended for vibration measurement and control, but that is only during construction phase. After that, it is not given. So, a lot of studies need to be done on this issue.
Yeah, the second question was, as I said, the microphone, change in the type of microphone for the sound meters.
The second part of the question, please, about the microphones.
Yeah, I say now, actually here now, online real-time noise measurement sensor should require for regular monitoring, not our regular sound level meters.
Okay, thank you.
Any other questions, please? Okay, thank you, Mr. Lokhande. Looks like you have ignited minds to ask very motivating questions. And a very
Thank you very
interesting
much.
talk.
Thank you.
And thank you so much for your time and an excellent presentation. And on behalf of all the participants and audience, I thank you personally.
Thank you.
And this brings us to the end of this session. And we are almost 10 minutes late. So we'll break for tea now. And I think the next session starts at. There is some printing error there. We have 15 minutes time for tea break. That's it.
Thank you, ma'am, for chairing the session. Now I would like to request Dr. S.R. Shukla, sir, to facilitate Dr. Neeta Dilawar, ma'am, with the momentum.
व्हाट्सएप आपका लॉगिन आप मेरे को भेज दो व्हाट्सएप पे आप तुरंत लॉगिन करो मैं आपका लॉगिन नहीं है हमारा मैं नंबर आपका सेव करूंगा फिर आपको लिंक दे दो.
Now we'll have a short tea break of 15 minutes, and all the online participants are requested to please join again in the online after sharp 15 minutes.
नहीं आप ले लो अभी फ्री टाइम में सब जाएंगे बाहर. ओके इसके बाद चार्जर रहने दो ना चार्जर अपनी है पासवर्ड